Welcome. This is to the classes of 86 through 90. This is a webinar brought to you by the class of 88 with a fairly informal meeting with Professor Deepto Chakrabarty, who is also class of 88 and who is now the head of the physics department at MIT. He received his bachelor's in physics alongside us in 1988 while living at Senior House, right, Deepto? I believe. And while it has taken me 40 years to understand quantum mechanics, apparently Deepto understood it the first time around, as proven by the fact that he went on and received his Ph.D. from Caltech in 1996. So at that point, returned to MIT, he's been there ever since, from what I understand, doing research in high energy astrophysics, think black holes and neutron stars. In 2022, he was named the new head of the physics department. So welcome, Deepto, and I'm going to turn this over to you and share some memories and let us know what's going on. And we'll have a Q&A at the end, but if anybody has any real pertinent questions to ask along the way, I'd say, go ahead and ask.
Great, thanks. So I have some slides. I hope that's okay. So I'm going to share my screen.
Sure.
Let me
do you need to make you host?
I don't think you need to make me host. Let me see if I can get this to work. Just go to the beginning there. Okay, are you seeing that?
Yes.
Great, and let me go to that. And okay, so great. All right, so first of all, thanks very much, Julian, for inviting me to do this. So I am going to spend about 20 minutes just telling you a little bit about some of the science that I work on, and then I'll spend about 20 minutes just talking about some of the changes that I've noticed and that you would see if you come to visit campus that have happened over the past 3.5 decades. And then we'll have about 20 minutes for questions. But of course, if you want to interrupt with something along the way, that's fine. So just to give you an idea of trajectory, so indeed, I was class of 1988, like many of you. When I graduated, I moved to Berkeley, where I spent 2 years working at the Lawrence Berkeley National Laboratory with the astrophysics group there as just a technical staff member. And then I went to Caltech for graduate school for 5 years, where in physics, where I worked in high energy astrophysics, as Julian was just saying. I came back to MIT as a postdoc in 1996, and I joined the faculty in 1999. So when I joined the faculty, or when I came back as a postdoc in 96, NASA was just launching a new X-ray satellite called the Rossi X-ray Timing Explorer. It's named after Bruno Rossi, who was an MIT physics professor and one of the founders of X-ray astronomy. And MIT helped to build some of the instruments on the spacecraft, and it did some of the early work that laid the foundation for the stuff I'll be talking about in the first 20 minutes. So, I haven't actually referenced my title here. So what I'll be talking about are millisecond X-ray pulsars and using neutron stars to do physics and astrophysics. And there's unfortunately only an artist rendition and not a real picture on the slide there, but that will give you an idea of what I'll be talking about. And I'll show you some animations that make that clearer. So just like hyper quick review about neutron stars. So first of all, ordinary stars like the sun support themselves by burning hydrogen and helium at their core. When they eventually burn out, they collapse, and depending upon how massive they are, that governs what happens to them at the end. Stars like our sun will collapse into something called a white dwarf. Stars that are more massive than around 20 solar masses when they're born will collapse into a black hole, sort of a gravitational singularity. But in between, sort of intermediate mass stars between around 8 and 20 times the mass of our sun, when they finish their nuclear burning, they collapse in what's called a supernova explosion that forms a neutron star. And a neutron star is something with the mass of around the sun, around 1.5 times the mass of the sun, but about the size of Boston. It's about 10 miles across. It is essentially a giant atomic nucleus. So all the protons and electrons have mostly been been pressured and inverse radiation decay to form neutrons. So you have a very neutron-rich thing. And it's basically the density of an atomic nucleus, but with a radius of around 10 kilometers. They're really, really weird objects. They're the densest objects that are known. A teaspoon of a neutron star would weigh many, many tons. And so that's the objects those are the sorts of objects that I study. Pulsars are a kind of neutron star. Many neutron stars have very strong magnetic fields and so rotating, highly magnetized neutron stars are called pulsars. I just told you that they're formed in these core collapse supernova explosions, and they're typically born spinning at a few tens of milliseconds, and with a surface field. I'll show you this on a graph in a second, but with a surface magnetic field about 1 trillion Gauss. And just to orient you, the Earth's magnetic field at the surface of the Earth is about half a Gauss. So a neutron star surface at birth typically has a magnetic field of like 1 trillion times the Earth's magnetic field. And then these pulsars are basically just spinning magnetic dipoles. And if you spin a magnetic dipole, if you spin a magnet, it radiates, and that electromagnetic radiation has to come from some reservoir of energy. The reservoir of energy is this rapid spin of the neutron star. So what will happen is if you just have a neutron star that's born and you just let it sit there, it will radiate away happily and it will slow down as it does that. Now, I said that these neutron stars are born spinning at a few tens of milliseconds. It turns out there's this, when they were first discovered, a very weird class of objects called millisecond pulsars, which are spinning at 1 or 2 or 3 milliseconds, so much faster than what we think the birth spin is, but they're also very old. And that's very confusing given the story I just told you, because if you're born spinning at a few tens of milliseconds and you just slow down as you radiate away energy, how would you ever have older objects that are spinning faster than the birth spin? It was a puzzle when they were first discovered, and one that lasted about 25 years. So I want to tell you about the story of how that works and how we figure that out. But first, let me just orient you with this diagram. So what I'm plotting here is the magnetic field strength of a neutron star on the y-axis and the spin period on the x-axis. And all those dots, don't worry about the lines, but the dots in the upper right-hand corner represent radio pulsars, just in various places. And the open circles at the lower end, lower left of the diagram, are these millisecond radio pulsars. You see they're spinning at about a few milliseconds. They have much weaker magnetic fields, only 10 to the 8 to 10 to the 9 Gauss instead of 10 to the 12 Gauss. So we think that neutron stars are born, there, like where that 1 is, spinning at a few tens of milliseconds and at 10 to the 12 Gauss. And as I told you, they just slow down because they radiate away their kinetic energy. So they evolve to the right on this diagram. Now, a curious thing, I'm not going to get into why this is, but more than half the stars in the galaxy are members of a binary. The sun's actually unusual in the sense that it's not. It's something about how stars form. They like to form in pairs. And so if a neutron star is in a binary and the binary isn't disrupted by the supernova explosion that makes the neutron star, then its binary companion might evolve to the point that as it evolves, it grows larger in size, that it basically overfills I don't want to say this, the surface within which it will stay bound, and it can start to leak matter onto the neutron star. Here's a picture of what that looks like. I'll show you an animation that shows this in a second, but what you're seeing here, and again, unfortunately, an artist rendition, on the left is the ordinary star that has evolved to the point that it's sort of overfilling its critical surface. On the right, that little dot at the center is a neutron star. And what's happened is that as the star on the left evolved and grew bigger, eventually the gravity from the neutron star started pulling mass off the regular star, and it leaks onto the neutron star. It doesn't, because the star is, or the two stars are orbiting around the current center of mass, that flow doesn't go straight to the neutron star. It has some orbital angular momentum. So it forms a disk. It's kind of like spinning down a drain into the sink, right? It doesn't go straight in. It forms a disk, and then because of friction, it slowly falls into the neutron star. And for reasons that I'll get to in a second, when the matter hits the neutron star, it emits X-ray radiation. You see this beam of X-rays comes out. Okay, I'm going to show you an animation that sort of takes about 100 million years of evolution into about 30 seconds and shows you all of that. But that's the basic picture. So I'm going to look at a diagram of this. So you have the same diagram, the same picture at the bottom there. At the top, this is an edge-on view of the center of the accretion disk. So the blue circle is a neutron star. Imagine that the magnetic axis of the neutron star is tilted a little bit, like the Earth's magnetic axis is with respect to the spin axis. And you see those dipolar field lines. And the red on either side, that's the disk flow of material that's in an orbit. At any given radius, it's in a roughly circular orbit, but it's slowly drifting inward. Now, what will happen, because the magnetic field of the neutron star is so strong, that there's a radius called the magnetospheric radius, where inside which the magnetic field is so strong that it starts to distort the flow in the accretion disk. You can think of it as the accretion disk is basically very hot, so the gas in it is ionized. It's like charged particles. When charged particles are in the presence of a strong magnetic field, they spiral around these field lines. It's called it's Larmor motion. And when the field is really, really strong, the spiral radius is so small that what basically happens is it's as if the gas just moves along the field lines. It can't move across anymore. It's moving in little circles around the field lines, but it's free to move along the field lines. So what that means in this magnetic situation, instead of the accretion disk gas accreting onto the entire neutron star, it moves along the field lines, and gravity is still pulling it, but it's only free to move along the field lines because it's a strong magnetic field. So it falls onto the poles. It doesn't fall all over the star. It only falls on the North Pole and the South Pole. So those spots are like hot spots because this material is falling. But because a neutron star, so a neutron star has the mass of the sun. So from far away, its gravity looks just like the gravity of the sun. But unlike the sun, it's only 10 kilometers in radius, which means you can fall a really long way before you hit anything. By the time you get to 10 kilometers from the center, you're moving at something like 1/10 the speed of light, and then you suddenly stop. Okay, that's a very, very energetic reaction. It gives rise to X-rays. So this is why you have X-ray pulsars. What happens is you're accreting this gas onto the neutron star. It's preferentially falling onto these poles, these hotspots, and then there are X-rays emitted from those hotspots. But because the axis is tilted, as if imagine you're far away, you're looking at this neutron star, you see one, or depending on the angle, both spots rotating around. And so you don't see steady emission. You see that spot coming in and out of your field of view as the star rotates. So you see pulses at the spin period of the neutron star in X-rays. That's why it's called an X-ray pulsar. Okay, so that's how they work. So what's nice about this is you can trace the rotation of the neutron star this way. And the other neat thing is that because neutron stars are so small in radius, if you think back to 801, there's a thing called the moment of inertia, which tells you how easy it is to spin something up or not. And it goes as the mass times the radius squared. So the radius of a neutron star is really small. So its moment of inertia is very small. So if you apply a torque to it, it will actually spin up a lot more than something with a larger radius and the same mass. So you can actually see changes in a neutron star spin period on intervals as short as days or weeks or months, basically a gratitude time scale. You don't have to wait decades the way you do for a white dwarf. You can actually, so I did my PhD thesis actually studying the spin evolution of slow neutron stars. And thank God they were neutron stars because I finished in 5 years, so that was good. So these are beautiful laboratories for studying this process of magnetic accretion, which happens in all sorts of different stars, not just neutron stars. Was there a question? No, okay. So one other thing that I want to add, as this accretion happens, it adds a little bit of mass to the neutron star. They get a little heavier. But more importantly, like I said, it changes the spin of the neutron star, it spins it up. And you can understand that as follows. Imagine, you go to a playground and you see one of those little like merry-go-round type things that kids like to run and spin on and get dizzy on and then throw up. Let's leave out the second part. So imagine it's one of those things is sort of turning around and you're running in a circle next to it, but you're running faster than the thing spinning. And now you jump onto the merry-go-round. if you're running faster, when you jump onto the merry-go-round, it will start rotating faster because your angular momentum has gotten added to the merry-go-round. On the other hand, if you were running slower, or even more, if you were just standing still and jumped onto the spinning merry-go-round, it would slow down because it would be trying to spin you up, and it would have to use some of its angular momentum because of that. So if the disk velocity when the accretion happens is faster than the rotational velocity of the neutron star will spin up. It will go faster, and that will happen until it reaches an equilibrium when the two velocities are the same, and then it'll stop. Okay, so here's now this picture I promised, is this animation that's going to show you a star starting to fill its Roche lobe, forming this disk, accreting onto the neutron star, making these X-ray pulses, and spinning up the neutron star. It's like 100 million years in about 30 seconds. So here we go. I'm hoping this will work. Let's see. There it goes. Okay, great. So here's the star orbiting around. Okay, there it's now starting to leak out. It's formed the disk. We're gonna. Okay, there's the X-ray emission happening because stuff is accreting onto the neutron star. We're gonna zoom in, and you'll see an illustration of the magnetic field of the neutron star truncating the inner part of the disk, and then channeling that flow onto the poles. And you see that stuff going on the poles. And if you watch carefully, you'll see the pulsar start spinning faster and faster. Okay, this is a cartoon, but it gives you an idea of what's going on. Okay. Oops. All right. So that was the thing I told you about. So we're born at point 1. We evolve to the right. You know, maybe tens of seconds. It can be very slow. The binary companion maybe forms this X-ray binary and starts accreting. When that happens, it starts spinning up the neutron star. So it moves back to the left on this diagram. Now I can tell you about this solid line, solid diagonal line. It's called the spin-up line. Okay. That's this equilibrium point. That's representative of when you reach the point where the accretion disk and the neutron star have the same angular velocity, so you can't spin up anymore. So this process that I just described to you would bring the pulsar back to around point 2 on this diagram, at which point you're like, okay, I'm done. So that tells you how you can spin something up back to a few tenths of a second, but not how you get to milliseconds. And so the piece that I'm missing is, it turns out, so this process of mass transfer can happen over a very long period of time, billions of years. And sustained accretion onto a neutron star, we now understand. We don't actually understand the detailed physics of why this happens, but it's clear observationally that process can bury the magnetic field of the neutron star and make the neutron star's magnetic field appear weaker. So notice, if I weaken the magnetic field to around 10 to the 8 Gauss, then the equilibrium spin period is a few milliseconds. So we think what happens is these X-ray binaries accrete for something like 1 billion years. During that time, they move along this path 3 down to the lower left. And at some point, when the mass transfer stops, because maybe you've just run out of mass or the binary detaches or whatever, you're left with these isolated, rapidly spinning millisecond radio pulsars, and that's how they're formed. So that was a theory that was made in the 80s as to how they were formed. The problem was no one could find any examples of an X-ray emitting system that emitted millisecond pulsations. Okay, people spent 25 years looking for that, and I am proud to say that our group co-discovered the first example of that in 1998, and we found the first millisecond X-ray pulsar, and so that confirmed this picture of how you make millisecond pulsars. And again, I just want to stress, millisecond pulsars are really phenomenally weird objects. They are spinning so fast that the surface of the neutron star is moving at something like 20% the speed of light. They're incredibly relativistic objects. They have all sorts of weird behaviors, which I'm not going to have time to go into today, but they're wonderful, wonderful laboratory. But it was a mystery as to how you made them, and now now 20 years ago, we demonstrated how that was done. So the question I want to ask now is, what sets how fast the neutron star can spin? Right, so you're dumping this matter on. As long as you don't run out of stuff, you can get it to go, you would think, arbitrarily fast. Now, nothing can spin arbitrarily fast. You know that if you have, let's say, a sphere with a certain mass or a certain radius and it's spinning, if you spin it fast enough, eventually stuff will start to fly off the surface. You'll tear it apart because of centrifugal stress. And for a given mass, what that maximum spin rate is depends upon what the radius is. The larger you make the radius, the slower that breakup spin rate is. So people don't know exactly what the interior of neutron star material looks like, but based on the kind of nuclear physics considerations, it was thought that the maximum spin rate of neutron stars should be around something around 1500 to 2000 hertz, 1500 to 2000 cycles per second. And so the question is, suppose now you looked at the distribution of millisecond pulsars, what would their spin distribution look like? And I've drawn in this very suggestive way. So I'm looking here at a particular class of millisecond pulsars, the ones that are these X-ray bright ones. And on the x-axis here, I have spin, and I go up to 2000 hertz. And the reason is because the instrument that we're using was capable of detecting X-ray pulsations up to 4000 hertz, but up to 2000 hertz without any loss in sensitivity. And what you see here is the set of all, like each little line is one system. And you see there's sort of a uniform distribution up to about, there's a little gap around 500, but that's just because there weren't that many systems. We have more now and it's filled in that gap. But what hasn't changed is there's nothing faster than about 700 hertz. Okay, that's a big puzzle. Like you should be able to spin these things up all the way to 1500 or 2000. Maybe in some systems you would run out of mass before you got there, but the calculation showed that there should be more than enough mass in these binaries to get up to 1500 to 2000. So that's very weird. And the question is why is that? So I'm not going to go through there was a whole debate for a decade about what's causing this weird cosmic speed limit. What I'm going to tell you is that what seemed to be the weirdest explanation is basically the only one that's left standing right now. That doesn't mean that it's right, but it's very exciting if it is true, which is the idea that there may be a limit imposed by the emission of gravitational waves. And let me talk about what I mean by that. So those of you who took 803 may remember that if you have an electric charge and you accelerate it, that it emits radiation. That's actually how electromagnetic radiation happens, from the acceleration of electric charges. So Einstein predicted in general relativity that there's a similar behavior with masses, that accelerated masses give rise to what's called gravitational radiation, which is essentially a ripple in the structure of space-time in relativity. Now, the effect is very weak, so it requires very high masses and high densities to observe. So normally it would require things like neutron stars or black holes. But one example of this that would be predicted is if you have a neutron star that has some even just small asymmetry in its core, and it's rotating, that rotation gives rise to an acceleration of this asymmetry that gives rise to gravitational waves. Gravitational waves carry away energy. Now, the energy output from a rotating neutron star giving gravitational waves, it's an incredibly steep function of the spin frequency. It goes as like spin frequency to the 5th power. Now, what that means is if you have a small asymmetry and you're rotating a neutron star slowly, it doesn't matter, it doesn't emit much energy. But imagine you had a dial and you could start dialing up the spin of the neutron star. Eventually, the radiation energy goes up as spin to the 5th. So what would happen is you'd see nothing. But at some point, you would reach a range where over a very narrow range in frequency, you'd go from gravitational waves not mattering to suddenly gravitational waves dominating the whole energy budget. It would happen very sharply because this frequency dependence is so steep. Now, the theory doesn't tell you what frequency that would happen at because it depends upon what kind of asymmetry is in the neutron star. But if 730 hertz happen to be the limit, that tells you something about neutron star structure. So the theory that some of us are backing is the idea that the speed limit is due to the fact that we're hitting a gravitational wave wall, basically, around 700 hertz, and that's preventing accretion from spinning up the neutron stars past that. So you may know that MIT, working with Caltech and a bunch of other institutions, was successful in making the first direct detections of gravitational waves from a different source, from merging neutron stars and merging black holes in 2015. It led to the Nobel Prize for our faculty colleague Ray Weiss in 2017. That was with an experiment called LIGO, the Laser Interferometry Gravitational Wave Observatory. One might hope one could use LIGO to measure gravitational waves from pulsars like what I'm describing. Unfortunately, it's a very, very difficult measurement to do, both because the signal is very weak. Unlike these, the things that LIGO discovered in 2015, they're not bright transients. They're continuous weak signals that have to be integrated over many years. People are looking for them, but it's years before we'll have the sensitivity to verify this. There are some other indirect ways that people can try and confirm this hypothesis, and we're working on those, but it will be years before we know for sure. So for now, we have a puzzle we think could be solved by gravitational waves. In the meantime, we have this weird speed limit that we don't entirely understand. That's an example of something that my group works on and I wanted to tell you about. I also just want to mention that the measurements that we're doing more recently, we're doing with this cool little experiment called NICER, the Neutron Star Composition Explorer, which is, instead of being a free-flying satellite, it's actually an experiment that's been placed on the space station. What's nice about that is it's much cheaper than launching a satellite, right? You just send your box up with the supplies going to the astronauts on the space station. You mount that on the space station, you plug it in, basically you have free power on the space station, and then you take data. So now the downside is there are astronauts going around doing stuff every once in a while, so you have to shut down your telescope now and then. But it's a very cheap way of running an X-ray experiment. This is something that MIT provided the detectors for. NASA Goddard Space Flight Center is running the overall mission. It's been running since 2017. It's been very successful. And this is something we're using to measure, among other things, emission from X-ray, millisecond X-ray pulsars. Okay, so that's what I wanted to tell you about the science. And I guess I have a summary slide here, but I'm going to move on now to tell you, just to talk a little bit about MIT and how it's changed since we were students there. So I want to begin with this headline, which you probably didn't see because it happened a few months before we arrived on campus, at least for class 1988. Trumpeting that class 1988 had the highest percentage of women ever in MIT history. That enormous percent was, I think, 29%. Let me just check my numbers here. Yes, 29%. So how does that compare to this year's freshman class? So let's just take a look at some statistics. So this is the class of 1988 versus the class of 2027. So in 1988, 71% men, 29% women, roughly 10% of what the NSF calls underrepresented minorities, so underrepresented in science and engineering. I couldn't dig up the number of international students in the class of 88. So for this year's freshman class, the class of 2027, a number I shudder to see because it just seems so big, roughly the same number of students. It is basically a 50-50 split between men and women. You'll see that doesn't quite add up to 100 because some people chose not to disclose their gender identity, and some people had a different gender identity because we are living in a somewhat different era now. A third of the students of the freshmen are from underrepresented minorities, and 10% are international students. So that's a significant demographic difference that we see in the classes. Again, from the tech, October 1985, this is what the class of 1988 declared as their major as of the 5th week of our sophomore year. Okay, so you can see this sort of split here, mostly in the School of Engineering. So by the way, there are two numbers on each one. The first number is class of 88, and the second number in italics is the class of 1987. So they're just giving a year-to-year comparison there. So I'm going to skip ahead to a table which shows the same thing, class of 1988, and for this year's sophomores, class of 2026. And so a few things I want to note. So first of all, still true that engineering is the largest part of the class. Some changes. So Aeroastro is down by about a factor of 2 over that time. There's this new Department of Biological Engineering, which did not exist when we were undergraduates. Chemical engineering is around the same. Civil engineering has gotten a bit smaller. Course 6 remains the big department, although the details have changed. So in 1988, course 6 was about 30% of the overall class, and 2/3 of course 6 was electrical engineering, and 1/3 was CS. Now that's really flipped. CS is a much larger fraction, and the overall number is half. If you skip down, I'm just going to look at in mathematics there, where it's doubled. That 127 in math includes course 18C, which is math with computer science. So if you include that, the computer science and AI majors at MIT are roughly 50% of the overall class. Not all in course 6, and actually not all in course 6 and course 18. There are some other majors that have done subject with a computational component as well. But it's up around 50% now. What are the other things that I want to show you on here? I think, well, those I guess other significant changes. So one thing is that in the life sciences, the number of biology majors has decreased significantly, but has been balanced by this new biological engineering major. So there's still a significant amount of life science work, but not all. And then in the Sloan School of Management, the number of undergraduates doing management degrees has increased a lot. By the way, I'm choosing the software majors because these are the primary majors. Many students are doing double majors. Many students are doing double majors, much more than when we were undergrads, and I'll get to that in a moment. But this represents the primary majors. If you look at the graduation requirements, although a lot of details have changed and what's covered in the individual subjects has evolved over time, as you would hope it would, the overall structure has not changed a lot. So the science GIRs, there are 6 subjects. Biology was added in 1990, shortly after the class of 88 graduated. But otherwise, that still looks the same. Math is 1801 and 1802. Physics is 801 and 802. Chemistry is some version of 511 or 3091 in material science and engineering. A significant change since we were undergraduates is that there's a much heftier communications requirement now, and this covers both written and oral communication. It requires 4 subjects a year. In the freshman and sophomore years, these subjects are done in HAS classes. The freshman one is typically a writing intensive class. There is still a freshman writing exam, so you can place out of that writing class if you pass the freshman writing exam. And then in your junior and senior years, you take a communication intensive course in your major. So it's specialized communication for your major. For example, you might be writing a technical paper, but also involving and learning to give presentations of technical material in your major. So that's something that's evolved over the years. Sorry, was there a question? No. Okay. So I think these other requirements are only have minor changes from what existed when we were students. The one thing I want to point out is, you may recall there was this rule that you had to have 180 units beyond the general institute requirements in order to graduate. And if you wanted to do a second degree, you had to have 90 more units beyond that. So you had to have 270 units to do 2 degrees. So that was MIT's way of making it hard to do 2 degrees. That policy changed about 15 or 20 years ago as the increase in interdisciplinary work really started to mean that it made sense for a lot of students to try and concentrate in more than one department. And so this 90 extra units per extra major was dropped. And as soon as that happened, you still have to satisfy all the requirements for the second major, but you don't have to have all these extra units. And that's much more workable. So more than half of our current undergraduates get a second degree in something. I'll be honest, I actually think MIT's made it a little bit too easy to get multiple degrees, because there's a little bit of a paper chase, or whatever the digital version of that is now, of like, oh, I should get a second degree because it looks more impressive. People overload in order to do that. But anyway, that is the case. It's representing all. The good part of that is it's enabling a lot more interdisciplinary study and innovation in a way that's been really good. Okay, so let me talk a little bit about how campus looks different. You may recognize this venerable diagram. I actually took it from the 1987-88 course catalog. I'm sorry, it looks funny in the middle. It was on 2 separate pages, and I had to try and glue them together. So this is what campus looked like back then. I want to focus in on central campus here, and in particular, let's see, if I move this, can you see me moving my mouse around?
Yes.
Okay, great. So I want to talk about the northeast corner here, which is what has changed the most. So you may remember this. So there was a big parking garage here. There was Building 20, this supposedly temporary shack built in World War II, which decades, which Cambridge then tried to declare a historical thing to prevent MIT from taking down, but that's another story. And in the upper right-hand corner here was a factory that belonged to TRW. It was a fasteners factory, I think. This northeast quadrant of central campus has changed immensely. So that's what I want to start out with, and then I'll talk about some other changes as well. So, okay, so this is what the new campus map looks like. And again, so now we're talking about this area here. You can see already there are these buildings here. There's this beautiful green area. It's very, very different than it looked like in the late 1980s. So this is the region I'm talking about. Let me start out with this building here, building 68. This opened very soon after we graduated. This is the new biology building. Okay, so that's what it looks like. It opened in 1991. Just north of it here, Building 76, is the Koch Institute for Integrative Cancer Research. It opened in 2010. That's this building here. So these two buildings together represent a lot of life sciences. Building 46 here is where the new Brain and Cognitive Science Complex was put in 2005. That is on Vassar Street. It looks like this. So between this, life sciences has a big presence in this northeast corner. If you visited the area, you know that this area around Kendall Square is now a hotbed of the biotechnology industry and pharmaceuticals. So life sciences has a huge footprint now in this area. Building 32 is the new Stata Center, well, new as of 2004. It's a Frank Gehry building. You may have seen it or seen photos of it. It is a very weird-looking building. It is where computer science and artificial intelligence is. This is what it looks like. It kind of looks well. I'll refrain from commenting on it, other than say it's very strange looking both outside and inside, but it's huge. The upper floors are where computer science and artificial intelligence are. There's also on the lower floors a lot of general institute stuff. So there are several large lecture halls, basically sort of similar to the size of 10250. So a lot of big classes meet there now. There's a new cafeteria there, basically replaces what had been the Walker Memorial dining area, is now here. A lot of student activities do stuff in this area. There's a lot of open study space. There's a gym attached here. So it's a major nexus of undergraduate activity, in addition to being in the upper floors, a center for computer science and artificial intelligence. Okay, and then Building 12 used to be sort of this low-rise thing that included the Career Center. It is now MIT Nano. It is a center for nanotechnology that was built and opened in 2018. It went rather over budget, and so it is somewhat empty right now because they are still recouping the money to sort of start putting in the equipment to have people move into it. But it is a state-of-the-art facility for nanotechnology. It is replacing a lot of what had been, for example, in Building 39, a lot of device physics and engineering stuff. So very, just phenomenal laboratory space that has been very important for MIT science and engineering. And then finally, across the street from the core 6 buildings like 36, 34, 38 is the new building 45, which just opened last year. This is the new Schwarzman College of Computing. You saw the huge numbers in terms of computer science related majors. Part of MIT's response to that was to create this Schwarzman College of Computing. It's called a college to distinguish it from the 5 schools, engineering and science and architectural planning, humanities, social sciences, and management. It's supposed to be sort of running perpendicular to them, that it is infusing computing in all the other disciplines at MIT, and it's sort of a common staging ground for that. That's at least how it was sold at the Institute. We're still sort of learning how it's going to play out, but it is a major new nexus for both for computer science generally, and for not just for straight CS research, but for, again, how CS, AI, and machine learning connect to all the other disciplines at MIT, which it does. Okay, let me move on to some changes on East Campus now. I'll go through this pretty quickly because I want to get to the last part. I'll just say building E14 is the new extension of the Media Lab. You may remember the original Media Lab opened basically in 1984, just as we were freshmen. So now there's this second building right adjacent to it. MIT, as part of the sort of substantial renovation of the whole Kendall Square area, MIT's built a new sort of Eastern Gateway, these buildings E28 and E38. So on the left here, this is MIT Medical. You may remember that. Kendall Square is over here. That's the Marriott Hotel that opened in 1986. So this building houses now the MIT Museum was moved here. You remember the old MIT Museum north of campus, which was just like, it was kind of like going to somebody's garage, and it was, it had some cool stuff, but it was not very well presented. The new museum is magnificent. It is absolutely fantastic. It has they've really thought about how to present material. It's not just MIT history. It's also a lot of stuff on science and technology generally. It's very popular. It's very crowded, and it's bringing a lot of people to campus to see. Adjacent to that, this building E38 is a new MIT Welcome Center. A lot of people arrive on campus, not at 77 Mass Ave, but on this side of campus, coming out of the Red Line or whatever, and they get there always to be like, wait, where is MIT? Where is it? I don't know how to find it. So this new gateway is sort of creating a major new presence for MIT. And this is actually, for example, where the admissions workshops and things happen now, is here instead of over in Building 3. And then I'll just mention there's a new fancy main building for the Sloan School of Management. I promised Sloan I'd mention that, so that was it. Okay, so let me talk about West Campus now. First, I'll just say in 2002 there was this new, beautiful new center for sports and fitness that attaches to the athletic center. This is the Zotzinger Center for Sports and Fitness. It's proven very popular with students and faculty and staff. It's very used. I want to talk about living groups though now. So a big change that happened in 2002 is, as of 2002, all freshmen have to live on campus. And this policy change happened because of a real tragedy that happened in 1997 with the death of a freshman during rush, due to an alcohol-related incident. And as part of the fallout from that, MIT decided that all freshmen were going to be housed on campus. Now, since something like 300 or 400 freshmen were typically living in fraternities and independent living groups, they couldn't do that right away. So it took several years to build the first new undergraduate dormitory, and that was Simmons Hall, which is so just to orient you here. So here's Amherst Valley. Here's all the West Campus dormitories. Here's Briggs Field. So this is the first new dormitory, W79 at Simmons Hall. It has a capacity of 350 students. So it kind of looks like a giant waffle. I mean, that's actually just descriptive. That's what it looks like. But that was the first of 2 major new dormitories. The second one is here, W46, which opened in 2020. It's called New Vassar. This has a capacity of 450 students. So it's enormous. Here's a view of it from across Briggs Field. It's, as you can see, it's a giant dormitory. And then another change that was made. So W1 here, this used to be Ashdown House, which was, as you may recall, was graduate housing. It needed substantial renovation, and that was happening at around this same time. The renovation was completed in 2011. It was renamed Massey Hall, and it was changed to an undergraduate dormitory. This has a capacity of 490 students. The reason the graduate students were not happy about losing this as a graduate space, although a new Ashdown graduate house was built north of campus, further away, MIT decided to prioritize placing undergraduates close to central campus. And so that's why this became an undergraduate house. At the same time, we lost 2 existing dormitories. Ethan, I know you're here, so you already know about this. So Bexley Hall, which was right here in what year was it? 2013, I think. Facilities discovered some sort of catastrophic water damage to the building that required them to close down the dormitory. When they went to try and repair it, they found that the damage was so substantial, and what was required to bring the building up to current codes for a dormitory was so substantial that MIT decided it was not cost effective to reconstruct it, and they sadly tore down the building. So it is now a park. Oops, sorry, I didn't mean to do that. But so Bexley was lost, but we did gain these 2 other new large dormitories. Then in 2017, under very controversial circumstances, Senior House was closed as an undergraduate dormitory. That is a long and complicated tale. I'm not really going to go into it here, but I'll just say that in 2017, it converted to a graduate house. So the building is still there. It is providing graduate housing now. That was a real loss to a lot of special communities within the institute undergraduate population, which are, hopefully reforming in other places. East Campus right now is still open. It is, as of 2023, it is closed for renovation. It is being renovated. That renovation is ongoing right now. I believe it is scheduled to reopen in 2025 or late 2024. Okay, so that's the end of my slides. So why don't I stop sharing and open things up for questions? I see there's stuff on the chat which I missed because I was I couldn't see those. Okay, so should I go to the chat first?
Yeah, so Dieter, first of all, thank you very much for joining us here and going through this presentation. It's very, very interesting stuff. Some things here that I'm sure most of us haven't even thought about over the years, right? Like pulsars and the neutron stars, but it was really, really cool. I just had one question real quick. I know when you're showing the majors, and there's definitely a shift, obviously, from like physical things, hardware, mechanical engineering, electrical to software, essentially, right?
Yes.
And so is MIT doing anything to try to somewhat reverse the trend? It seems to me if the United States wants to bring manufacturing back to the US, we need people who know how to do physical things, right?
Yes.
So
absolutely.
Yeah.
So one thing that MIT has been doing that's been positive in the space is that they have been sort of trying to upgrade and increase the number of maker spaces around campus to get undergraduates sort of working with their hands again, making better access to it, access to things like 3D printing and just sort of revitalizing what had been becoming sort of moribund over a certain period of time. And that's been very popular. But you're right, it hasn't directly been reflected in the majors. There's a lot more people going towards software and digital stuff. Now, of course, I didn't actually talk about this explicitly, but a giant change on campus in every discipline is just the advent of digital tools, and it suffuses everything. And high performance computing is something that is being used even in a lot of areas of humanities and social sciences. So, but you are right. I mean, like we see this in physics, that the number of people who they complain about any experimental physics that they have to do as part of the major. We make them do it anyway, but it is a problem. And in particular in the 1980s, when people arrived on campus, many, not everybody, but many freshmen had experience with building things or working on stuff with their hands. They used to work on building stuff in kits. Most people knew how to solder. Maybe they worked on their cars, maybe not successfully, but at least they tried. And there's much less of that now. Yeah. So there's much less of that. People arrive not having played with things and being afraid to play with things, afraid to take things apart. So a lot of what we've been doing, things like in freshman seminars and in some courses, is just getting people to play with equipment and start getting that facility with playing with your hands again. And it's very popular with some undergraduates, some of whom have never done it before coming to campus, which again is weird to us, but that's just what life is like now. We're just trying to make the barriers to that much lower.
I think Mark had a question. You raised your hand. Mark, you want to ask a question?
Sure. Does the orientation of the pulsar relative to the galactic plane have an impact?
The orientation of the pulsar relative to the galactic plane. What mainly matters, do you mean have an impact on our ability to observe it, or an impact on what happens in the pulsar?
Well, that and the timing, because if it's oriented differently, then the bursts will potentially have a different speed. An observed speed.
Right. So I guess I'll say the orientation of the pulsar does matter to what we were able to observe. So for example, if we're looking at it basically pole on, we won't see any pulsations because the rotation is not changing our line of sight observation of the hotspot. So that matters. But locally, the neutron star doesn't care which way it's oriented with respect to us or with respect to the galaxy. It just does its thing. Does that make sense? It's not interacting with the galaxy in any way. It's just a local effect. But it does affect what we're able to observe. Yes.
Yeah, that was my question.
Yeah.
We do have a question from Michael Orkish. Go ahead, Michael.
You were mentioning the Rossi Explorer.
Mm-hmm.
I remember when I was a freshman, I was working for Professor Hale Bratton, was running X-ray timing Explorer. I was wondering.
Yes, that's the same
thing.
That's the same thing. After launch, NASA tends to name experiments. So what was the X-ray timing Explorer before launch in December 1995 became the Rossi X-ray timing Explorer. Hale Brat was in fact my postdoctoral mentor, and he's retired but still around.
So when you were at Caltech, you said?
I was at Caltech from 1990 to 1995.
Mm-hmm. Did you work with Kip Thorne?
I did not, because I was not a theorist. I worked with Tom Prince on observational high-energy astrophysics.
Mm-hmm.
All right, so Jim Casamenta, you've got a question? Raise your hand.
Yeah, D2. I'm curious, we've all been reading in the news about the tension on campus coming as a result of the Israeli Hamas war, Palestinian students, Jewish students feeling uncomfortable on campus. My question for you is, do you sense that tension on campus at MIT, or do you have any other comments or reactions about?
Sure. No, I'm happy to address that. So what I will say is that in the fall, there was absolutely, definitely a lot of tension on campus. So I would say, October, November, early December was very tense. First the shock of the horrific original Hamas attacks on Israel, then the mounting death toll from the Israeli response in Gaza. There was a lot of unrest on campus. There was a lot of protest. A lot of the protest was coming from people outside of campus who were coming onto campus, and that was making it harder to control the situation. It is definitely true that Jewish and Israeli students on campus, many of them felt very unsafe because of what was a very fraught environment. Now, things quieted down a bit after December, and January IEP and early February has been quieter. There is still tension on campus. I think it is considerably reduced. I think the feeling of lack of safety, I think, has been is at least from the students in the physics department that I talked to, they are not reporting feeling unsafe on campus in a way that they did in the fall. One of the things that I know in particular Jewish and Israeli students have been frustrated about is that they felt like many of the protesters were breaking institute rules seemingly with impunity and not facing any consequences because of that. Now, the fact is, as was true in the 1980s, the university disciplinary process is very, very slow and is largely confidential. So the problem is, if something's happening, you don't know about it and you may not know what's happened. So what I can say is that there are something like 50 or 60 disciplinary hearings going on right now, and also some of which had happened during the fall, in response to things that happened in the fall and as recently as a few weeks ago. And those things are going through the system. But that's not, the problem is, it's not like in the when something happens in a criminal court and you get to read about it in the news and everybody knows what the outcome is. Because of federal law, the outcome of these disciplinary things is largely kept private. And so that, I know, has been a source of frustration to many of the students that I've talked to, that they have no way of knowing whether anybody's getting in trouble for breaking the rules. And they feel like if people don't get in trouble for breaking the rules, then they are still at risk because people can still then do inappropriate things with impunity. And I totally understand that concern. It's a really difficult problem. I will say that I think the situation has improved. There's still a lot of strong feeling about what's going on from many different sides, both in the Middle East and on campus. Of course, you can be upset about what's going on in the Middle East without mistreating your colleagues on campus. And that's a message that apparently some people are being a little bit slow to learn. The Institute is doing its best to try and address that. I think that as an institute, it's not clear to me that we handle all of that as well as we could have in the fall. I know that one thing that Sally Kornbluth, our new president, has done is instituted training on dealing with anti-Semitism for senior administrators and student affairs and diversity officers and things like that, so that we will do better on those things. And that's ongoing right now.
Thank you.
So a couple of questions. You made a mention about Walker Memorial. Did it close as a dining hall, or?
It closed as a dining hall. It's still, so I'll be honest, I don't know why it closed as a dining hall. I always really liked eating there, so I was actually quite annoyed when it closed as a dining hall.
Right.
But I think part of it was that there was the need for dining facilities on that side of campus exceeded what Walker was capable of doing. And rather than run Walker and the Stata one together, they decided to just run the Stata one. And now the Walker one. So Walker Memorial is still there. It's still used by student groups as student space. There's still the gym up on the 5th floor where we also still give 801 and 802 exams. But it's no longer an active dining hall.
I got a question about co-ops. I got a question about co-ops. So my son's hi Dito, this is Joe Harrington.
Hi Joe.
Hey, so my son's a junior at Northeastern right now. And of course, being a good alum, I was trying to convince him that maybe he should at least look at MIT. He had no interest whatsoever. At MIT, Harvard, Stanford, any of those, he wanted to go to a place where you would get a lot of practical experience. And his interest is in business and finance, so Sloan School would have been a good match. But he wanted a place that he would have a lot of practical experience. And at Northeastern, they really emphasized co-ops. In the spring of his sophomore year, he worked at an investment bank in Phoenix. And he was actually, helping companies sell themselves, right? They were on the sell side. So they were working with software companies, and he was actually doing, it was a small company, he was actually doing a lot of the work himself. He got an amazing experience. Just won a national investing championship, beating out, all the named schools. The Northeastern crowd is cleaning up on this, and Northeastern's a fine school, but I don't think of them as in the same category as, MIT, the Ivy, Stanford, et cetera. And yet, when I talk to a lot of the young folks at my school, I teach at University of Central Florida, they are very much looking for work experience that will get them hired. Now, MIT students aren't going to have any problem getting jobs, but that seems to be an emphasis. It also seems part of the national trend where a lot of young men are not thinking of college as something that's going to help them get a job. And it's weird because it's not paralleled with the women, but it's something like 55-45 female to male ratio in college right now nationally. So I'm curious, what's MIT's take on all this? We've always had UROP, which was research on campus. What about off-campus experiences for undergraduates, work experience as part of school?
So thanks for your question. So let me start by saying something about Northeastern, which is, those of you who only know Northeastern from what it was like when we were undergraduates, I think would be very surprised at Northeastern today, which is a very different university.
Very different place.
Shot up in terms of its reputation and its quality, and in particular, their internship program is phenomenal, and it's a real special thing that they do. So I'm not surprised to hear you say that your son is really impressed by it. So a few things I'll say. So in terms of internship and work opportunities for undergraduates, that has always been something that has been an area of some emphasis for departments in the School of Engineering, and that continues to be true. We have more MIT undergraduates interested in doing that sort of internship, either with companies or with national labs than was the case 30 years ago, but it's still relatively small. For the most part, people in physics who want to do internships, it's because they want to explore non-physics work opportunities, like working in finance or something like that. If they want to do research, they do UROPs, or they try and get an NSF opportunity somewhere else. So since physics doesn't have a big internship crowd at the undergraduate level, I don't have a lot to say. I don't have a lot of visibility into it. I do know it is a major component of some engineering department undergraduate programs. At the graduate level, we're seeing a lot more interest in internships, including in physics, and that's something that's developed quite significantly over the last 10 or 15 years, but not so much at the undergrad level. I'm afraid we don't have a lot more to say about that.
All right, we're at 5:05, so Deepto, I really do appreciate again you coming to join us. I do want to point out to everybody in the chat, Wendy has put a link. If you have any suggestions for future webinar topics, go to that link and let us know. Is there any pressing questions from anybody else? Otherwise, we will.
Let me just say, if anybody has any questions that I didn't get to that you'd like to direct to me, please feel free to send me an email it's deepto@mit.edu. It's really easy to remember. So just send me a note. I'll be happy to try and address it.
Yeah, super. Well, thanks again.
It was great seeing everyone.
Absolutely. All right. Thank you very much. Have a good
Thank you.
rest of the
Goodbye.
week.